All right, let's try another example. We're going to evaluate these integrals by interpreting each of them in terms of area. So for this first one, we're integrating from 0 to 2, and the function here is the square root of 4 minus x squared. So we've actually graphed our square root function here. This is the graph of square root 4 minus x squared. And so if we're looking at the integral from 0 to 2, really what we're doing is we're trying to calculate the area for this shaded region. So we're looking at the region that starts at x equals 0 and is under the curve, and then it ends at x equals 2. So we're really looking at this interval for x between 0 and 2. And we're looking at this region here. Now this function, this square root function, let's investigate that a little bit further. So what is going on with this square root? You might be able to tell from the graph here. So let's look at this function. Let's just set it equal to y. And if we square both sides and add x squared to the other side, we get x squared plus y squared is equal to 4. And this might be a recognizable equation. This is the equation of a circle with radius 4, or radius 2 rather, centered at the origin. So you can kind of see we have our center point here, and it's only the top half of the circle, and it's a circle of radius 2. If you count, from this point to this point, what's the distance between those 2 points? Well, it's 2 units. So this is the this equation in general is just a circle with radius 2 centered at the origin, and the fact that we're using the positive square root here means it's the top half. It's the top half of our circle. All right, so what this integral represents is it's just the area of a portion of our circle. So this is just the area of 1/4 of a circle. All right, so what's the area of a circle? Well, it's pi r squared. So our radius is 2. And it's just 1/4 of that because, this is 1/4 of our circle. We have the top half, and then there's the bottom half as well. So this shaded region just represents 1/4 of our circle. So we're just finding that area. So the pi r squared here, this would be the area of the entire circle, and then we're just adjusting by 1/4. And if we do the calculation, this just ends up being pi. All right, so we can calculate this definite integral. We didn't have to do any antiderivatives, so kind of lucky. We could just interpret it as an area. Let's try another one of these. Let's look at this integral of x minus 1 from 0 to 3. And we want to interpret this region, or we want to interpret this integral in terms of area. So we have our function graphed. This is the graph of x minus 1, so it's just a line. And we look at our definite integral. We're going from 0 to 3. So that means starting at x equals 0 and going till x equals 3. And so we're looking at this shaded region, conceivably. And by calculating this definite integral, this is just the net area, which is the area above the x-axis minus the area that sits below the x-axis. So if we have a function that, over the course of this section of the x-axis, we're going from 0 to 3, during that entire interval, if this function, there's a section that goes below and there's a section that goes above, well then that represents the net area. And so the net area is the area above minus the area below. And so we can actually calculate these. And we can really do it with a little bit of geometry. So this is a triangle and this is a triangle, so we can just calculate these directly. So for this area above, well, it's a triangle with the base is 2 and the height is 2 as well. And then this, for this region that's below, if we look at this little triangle right here, well, the base is 1 and the height is 1. So formula for a triangle, or area of a triangle, 1/2 base times height. So 1/2 2 times 2 minus 1/2 1 times 1. And so we end up with 2 minus 1/2, which is 3/2. So that would be the value for this definite integral. So kind of what we're doing is we're looking at this area that's above, and we're subtracting off this area that's below. So you can almost think of it as sort of like we're looking at sections of the graph that kind of balance each other out. So in some way, let me get rid of this. In some way, this little region here, this little triangular region here, is like balancing out this little triangular region here. So we have a negative section, we have a positive section, and they perfectly balance each other out. And so what we're looking at is kind of what's left over, what the net result is. So there's this section here that doesn't get canceled out. And you can see this section here, this is a little square, so that has area 1 and then 1/2. The net area here is 3/2. So you can think of it as sort of like this area below is canceling out some of the area that's above, and we're just looking at, well, what's left over. So some kind of fun games to play here with areas and definite integrals.